Hey everyone, welcome back to the series. In the last episode, we calculated the loss using binary cross-entropy and backpropagated the gradients through our network. In this video, we're going to finish building the train method by accumulating gradients across each batch and updating the weights and biases. Let's get right into it. First, we accumulate the gradients across the mini-batch, and we're looping backward through the network from the last hidden layer to the first like this. For int L equals, inside parentheses, static underscore cast int layers.size -2, and L greater than equals 0 and minus L. Now we get a reference to the activation values of the neurons in the current layer, which is a vector of activation values. And here we say const std vector double reference activations equals, inside parentheses, L equals 0 and question mark inputs square brackets k colon layers square brackets L dot A. And this means if we're at the first layer, the input layer, the activations come directly from the input data. Otherwise, we use the activations from the layer itself. Inside this loop, we calculate the gradient for each weight by looping through all connections between neurons. And here we say for size underscore ti equals 0, I less than weight underscore batch underscore gradients square brackets L dot get rows and plus I. And then for size underscore tj equals 0, j less than weight underscore batch underscore gradients square brackets L dot get calls plus j. For every connection between neurons, we multiply the activation from the previous layer by the gradient from the next. Weight underscore batch underscore gradients square brackets L I comma j plus equals layers square brackets L plus 1 dot gradient square bracket j times activations square brackets I. This tells us how much each weight contributed to the overall error, and we accumulate it over the batch. After handling the weights, we also need to accumulate the gradients for the biases. And here we say for size underscore ti equals 0, I less than layers square brackets L plus 1 that size and plus I. And inside the loop, bias underscore batch underscore gradients square brackets L square brackets I plus equals layers square brackets L plus 1 dot gradient square brackets I. Each bias receives its corresponding error signal directly. We simply sum it up over the batch. Once we have accumulated the gradients, we update the weights and biases. Again, we loop through the layers in reverse, starting from the last hidden layer. For int L equals, inside parentheses, static underscore cast int layers.size -2 and L greater than or equal to 0 and minus L. Now let's loop through and update the weights. For size underscore ti equals 0, I less than weight square brackets L dot get rows plus plus I. And for size underscore tj equals 0, j less than weights square brackets L dot get calls plus plus j. And here we're going to update the weights. Weight square brackets L inside parentheses I comma j minus equals learning rate times inside parentheses weight underscore batch underscore gradients square brackets L I comma j divided by actual underscore batch underscore size. Here's what's happening. We divided the accumulated gradient by the batch size to get the average gradient. Then we multiplied by the learning rate. Finally, we subtracted from the current weight. This is how learning happens. And it's time to update the biases. For size underscore ti equals 0, I less than layers square brackets L plus 1 that size plus plus I. And inside the loop we say layers square brackets L plus 1 dot bias square brackets I minus equals learning underscore rate times inside parentheses bias underscore batch underscore gradients square brackets L square brackets I divided by actual underscore batch underscore size. Same idea here. We loop through the neurons in the next layer. Since we're looping backward from the last hidden layer, we use layers square brackets L plus 1 to make sure we also update the biases in the output layer. We average the batch gradients, scale them by learning rate, and subtract from each bias. Next, we log and print the training progress every 100 epochs, and we say if verbose and epoch mod 100 equals 0, we print the training progress. First, we declare a string stream, std string stream, and we're gonna call it data. And here's what we want to print. And then we say stdcout data.str and L scope log, and we pass in data.str. This gives us a nice summary of training progress, how many epochs are done, and the current binary cross-entropy loss. Finally, when all epochs are complete, we print the final states. Here we say arrow int equals std scope chrono scope high underscore resolution underscore clock scope now. This captures the in time, so we can compute the total training duration. And finally, we log the final loss and the total time it took to train, useful for performance tuning and benchmarking. And that wraps up the train method. In this video, we implemented gradient accumulation over mini batches, weight and bias updates using SGD, and helpful logging to track our training progress. If you found this helpful, make sure to like the video, subscribe to the channel, and turn on notifications so you don't miss the next episodes. In the next video, we'll implement 2 methods for saving and loading the model, and we're going to finish up our neural network.hpp file. You can download all the project files, including the dataset, source code, and log files from my GitHub. The link is in the video description. Thanks for watching, and I'll see you in the next one.